We're going to be moving on to our next speaker, whose topic is Architecture of Galactic Harbors, Transportation System and Enterprise Enabler. That is Mr. Michael Fitzgerald. Mr. Fitzer served in the United States Air Force from 1968 until 1990. After graduating from the United States Air Force Academy and serving in Vietnam, he returned to Los Angeles. There, he joined the United States Air Force Space Effort, and for 20 years in the Air Force, Fitzer has worked on major space development projects. Among these, he co-authored Today's Space Elevator and 5 other major reports on space infrastructure. He is working on publishing his 36 architecture notes and the Galactic Harbor. About the Galactic Harbor. So help me in welcoming Mr. Michael Fitzgerald.
Let me tell you what the story is real quick. About 7 years ago, Pete Swan called me and said, Fisher, we need to talk to a bunch of people that are working on a thing called the space elevator. And we need to get over the hump of what is the space elevator and how does it work. In that context, Pete and I and several others came up with the notion of next chart of exactly what we're going to do, okay? And it ends up being the Galactic Harbor. I love to tell the destination at the start, not at the end, and that's what I'm doing here. All right, next chart. This is one of my favorite charts. This is a picture from Google Maps, I think, Google Earth, of the Los Angeles Long Beach Harbor. And Vern Hall is going to follow me soon. He is the chief engineer of the redefinition of these two harbors. They're separate harbors, and he was in charge of the Los Angeles half. These are sister cities that never liked each other. But the point is, I live just off the upper left-hand side of this picture, and Vern Hall lives just off to the lower left-hand side. And I arrived in Los Angeles in 1974, and I have been driving past or through this harbor for 40 plus years. The transformation was magnificent. And the secret of Vern pulling this off, as it were, and his partners over in Long Beach pulling this off was simple. He had authority to do so. He and his team. And I want you to remember that for the rest of the morning. And this is sort of serendipitous in the sense that Kevin and Jerry and David have already told you, we got to do this. This is essential. I humbly point to this picture of, we've done this before. Next chart. Please. There you go. All right. The first thing we did is we need to differentiate between what we're doing and what we envision. If you go back in your mind as to look at that harbor, there is a main channel in every harbor in the universe, although I've only checked on the planet Earth. The space elevator transportation system is the main channel of the Galactic Harbor. The rest of the Galactic Harbor, which is all that stuff you saw that was dirt in my image, that's where the enterprises live. So I'm about to tell you what is the baseline space elevator transportation system based on the vision that there will be a Galactic Harbor. Okay, next chart, please. And what we did was we said, I know where I'm going when I get the transportation system, but I'm going to worry about the transportation first. And the notion of what you see there is a 100,000 kilometer tall harbor, quote unquote, or main channel, if you will. And that's it. That's what we're talking about. And the simple argument is, with the Adrian will show you here in a few minutes, a strong enough tether or tether subsystem, as I say with a wink to my friend Adrian, that we can do this now. All right, so we're building let me do it this way. We're going to start with the apex up at the top. It is the counterweight. That is where things leave. I'll show you that in a moment. The GEO Region, that's where the businesses will be. And the Earthport, which is the transportation nexus, between Earth's transportation system and the Galactic Harbour transportation system. There are 14 kilometers on our baseline, 7 going up, 7 going down, doesn't matter. Just keep the mass balanced, and a tether on the left-hand side and right-hand side. Now, the initial ops will be, well, skip that. I'll get to that later. All right, next chart. So I'm going to describe what is the transportation system. This is Vern Hall's baby. It is the Earthport Floating Operations Platform, and if you ask me why they have a floating operations platform, it's because that's what we need to make things happen. Okay? And I'm going to hang up on this guy so he doesn't interrupt me again. Now, the floating ops platform is the nexus between the transportation system of the world, and look, it is container shipping compatible. Next chart. Down at the lower, the kind of the wharf level or the arena, the surface level, and you'll see a bunch of room. You know, the doors open on 2 of them, and there's 13 or 14 of those. And they're all clean room capable, and they're putting the stuff, the cargo, onto pallets, and they're going to slip it onto a small going barge sort of thing, and they take it over to the tether, and we'll send it up the tether. Now, let's think about this for a millisecond. This place is a permanent place. We may send one out after a couple of years and change it out like it changed cruise ships, but this is the nexus of the planet Earth's transportation. We're taking stuff headed to the GEO or to the apex or elsewhere in the solar system. Next chart. The upper floors of what I just showed you is the op center. Need I say more? And I'll say a bit more in a few charts. Every single thing on every single climber is tracked via this operations center. Every single thing that's flying around inside the Galactic Harbour, and I'll show you that in a moment, is tracked at this operations center. This is the frontline operations center. The headquarters operations center is over on Access City, and I'll get to that, or Vern will get to that in his presentation. Next chart. This is the baseline. There's nothing here that needs to be technologically invented. Okay, next is the GEO Region. Next chart. What I've selected here is the imagery of the graphic that I put together actually 3 years ago, I think, Pete, right? And everything up at the GEO Region is, quote, attached, if you will, to the geosynchronous belt, the GEO belt. I show green orbits. There should be figure eights, but I ain't good enough artist to show a figure eight. The green are surveillance satellites, small CubeSats that are running around making sure that everything in this region is where it's supposed to be. Now let's take a look at this region. Notice. When I came aboard in 2013 or so, or 14 maybe, the GEO part of the space elevator was one satellite at GEO about 400 meters across, if I remember. This is 200 to 300 kilometers across and approximately 400 kilometers up and down. I know there's no up in space, but you get my drift. In other words, this thing is bigger than the state of California. And that is where the enterprises will be. That is where the power, space-based power stuff will be, in that blue cylinder. Next chart. This is our baseline vision. The apex region, next chart, is where things arrive and depart. And they go interplanetary. And now Pete Swan has described the fact that at 100,000 kilometers, you depart at 7.76 kilometers per second. And that's enough delta V, if properly guided, that's a customer responsibility, it can get to Mars. Now, that is an amazing baseline. And when we talk about a preliminary technology readiness assessment, which is where we're at, ready to start into phase B, okay, we're ready. Start engineering what you're seeing in the last three charts. All right, next chart, please. Now, we're not done. We can't do everything. So we're expecting the business community to do some things. In the terminology of architecture engineering, they're called adjuncts. In other words, to make simple, if you build a car, you're kind of expecting that there'll be a gas station around there somewhere. If you're building an electric vehicle, you're expecting that there will be recharging stations, if only in your own garage and elsewhere. That's an adjunct. We have three adjuncts at a minimum, and let's go through these, and this is very quick. And each of these is worth a master's thesis. Next chart, please. The first, there are three of them. And I kind of forget. Let's go to the next chart, please. This is the space debris adjunct. I wrote about it in architecture note number 25. It's online, et cetera, et cetera. There are four sub-functions that are going to be provided. And most importantly is the fourth one down, is that there is an active defense. We had a handshake with Jerome Pearson, rest his soul. And he recognized that if we were going to be a space elevator, then we needed an active defense component, but that was going to be provided by what the U.S. Space Force has in mind. And that program, called EDDI, is underway. They're having an operational flight sometime the next 18 months. They're having arguments with themselves about exactly which flight they're on. In other words, the space elevator has addressed, quote unquote, the debris problem. I described that in Architecture Note 25, and this adjunct is part of our baseline. All right, next chart. Everybody in this room undoubtedly has heard about space situational awareness. We are part of that. We are an anchor user. The Combined Space Operations Center in this adjunct will advise us when things enter or even approach the various regions that I just showed you. They will be actively tagged. I don't want to go through that in any depth, but we're going to keep track of these things. And if they don't do what they're supposed to do, actions will be taken. Not by the space elevator people, but by the Space Operations Center. This asset, the Galactic Harbour, is important and will be defended by the Space Force. Now, with all due frankness, there's an international context here because the Galactic Harbour will be an international thing. That part of this adjunct is not resolved. I don't mean to say I'm solved everything here, but in the baseline sense, I've talked to people that I've known at the one-star level, and they said assets in space will be protected. We have a policy problem, but other than that, we're cool. Top of that, chart 18 will show. Fabio's looking for his button, I think. There you go. Anything that's sent to the Earth port to go up the climber to get to either the GEO or the apex, we need to know what it is. So we have a very aggressive tracked plan, support, and management of stuff that's entering the Galactic Harbour via the transportation nexus. Okay, that activity is housed in the access city, and Vern will explain that when it gets to his turn, which I intend to be quickly. In other words, if some robot, if you know what I mean, up at GEO, okay, needs a wrench, even the wrench will be tracked inside the pallet that is assembled at the airport, inserted into the climber, and dropped off at GEO. Now let me segue here just a little bit. I have not talked about the enterprise system. That wrench will go to the enterprise, and it'll be taken to the place where somebody is doing satellite repair. Now, I make this a very simplistic point, is that we're there to service the enterprise. And I think that goes to the heart of what Kevin Barry was saying, is that nobody's going to pay for there to be a transportation system if it doesn't go anywhere and doesn't transport anything. Well, we're addressing that in the manner in which we baseline the Galactic Harbour. And one more thought after is this is only the baseline. Between you and me and the fence post, if you know what I mean, we have several alternatives. We have a multi-stage space elevator. We have a thing I lovingly call the 5-leg tripod. We have, I tease Adrian all the time about I need a slightly different tether because I want to know what's going on, etc. Well, this is an active activity. And we're, for example, we're having meetings, weekly, Adrian, on the climber tether interface study to figure out exactly how much traction we're going to get in what Yuri and Jerome figured out was the best way to get to space, which is a traction technique. We have baselined this. Now, with all due humility, and not much really, but the point I'm trying to make, 2 times in my career, I have started programs that are larger than the $15 billion necessary for a space elevator transportation system. I've seen it. I've tasted it. I know what it takes, and I'm not bragging. I'm pleading. We need to do this. It's essential. End of thought. How's my time? I lost track a little bit. Go to 19 here, Fabio, please. I'll take questions if I can hear them. If I don't hear them, I don't plan on answering them. Oh, yeah, my pretty picture. We are bringing the third dimension to the transportation network. And I think that's the theme of Vern's presentation. All right, I'm done with this one. Okay. Bill Britton's got questions. He's writing rapidly, but we'll get him later. Adrian's probably going to pick on me later.
Hey, Fitzer, just before we lost that slide there, I thought I'd just add one little other piece to build on the conversation. Those shipping containers you were showing have actually been incredible as a demonstration of how useful they are, and that it's been observed that the advent of shipping containers has had a greater effect on globalization than all of the free trade agreements that have happened since World War II, because it was the first time we saw a reduction in the cost of shipping in thousands of years of naval trade. And that by carrying that paradigm through to applying it to space, you would have those similar kind of gains.
Kevin, during my presentation, I was going to quote you, so you've kind of preempted me, but absolutely right.
My other presentation is, frankly, a long story about how much testing is to be required. These dispersed mega projects, and I'm talking about something, first of all, bigger than California and 10 Californias away. We have to test everything massively. And my other presentation, which Dr. Swan, I think we ought to skip, frankly, because it simply reinforces the fact that if you decide that you know what to build and have enough competence to test it inside out, you'll get to where you're going. All right? If you can test what you think you see, then you'll get to where you're going. Go to number 3. You know it's me, so what the heck? One of the things that ISEC really is absorbing here is the notion that we need to take a look at the system engineering problem of a thing this big. So we're calling it architecture engineering. And with all due humility, I have used architecture engineering for the last 15 years. Bill Britton and I use it on something we don't talk about. The notion is in the first bullet on the right-hand side, we are assembling the incompatible. What can be possibly more incompatible than something in the middle of the Pacific Ocean that we're struggling to keep from moving, and something departing the apex going at 7.7 clicks per second? The answer to that question is that we build intelligent interfaces, we do modeling and simulation, and we don't change out things, we evolve things. Okay, click. Next chart, please. We resolve this notion of assembling the incompatible, and this includes all of the segments in the transportation system, by enforcing or creating intelligent interfaces. And what they are is information exchange requirements, but they have been muscled up with artificial intelligence. And the artificial intelligence is built on the next bullet. Data collected during development and operational testing and modeled and updated constantly with operational data. Okay? Now, you go talk to some vice president, he's going to say, jeepers. I'm sorry. With all due respect, this is being done now. It's called cookies. Y'all know this. Next chart. What we're trying to enforce is that anything that happens in the transportation system, if it affects the behavior of something else in the transportation system, the affected system must be notified. I thought Bill Britton would faint when he saw this, because he's been in ops management for probably longer than he's like to admit. But that's the essence of the manner in which we're intending on building space elevator in the Galactic Harbour. Next one, chart 8. Let's go to the next chart. This is the notion of the sequences. Usually when you build something, you have a system requirements review, a data review, and then you have a design review. Now, because we're doing all this testing to proceed, we got to get the testing fast, quickly. And that's what the sequences represent. We will do single string testing. There's a long story. We will do, if anybody's ever been involved in a major project, there's this thing called thread testing. Still good and nodding. Thread testing. Thank you, sir. We're going to do operational testing, operational mode testing. We're going to, disaster event testing. Jeepers. And then finally, we get to sequence 5, and that's like spring training. We go out and we practice all the various kinds of testing, all the various kinds of operations, all of the what ifs that my foreman tells me I need to worry about. And that's in segment 5. Now, between you and me, as the saying goes, you don't leave limited operational capability, segment 5, until you're done. But on the other hand, at the beginning of limited operational capability, segment 5, you can start doing business. So if you have something important to deliver to GEO or to the apex, you can do it in segment 5. All right, so Tim Crispin asked me, I don't know when he asked me this first, but I'm going to say it now. He said, how much do you need and when can you start operating? I said, 10 to 12 billion. No, I said 10 to 15 billion in 10 to 12 years. And that's what segment 5 is. Okay, Michael?
Okay.
All right, you see what I mean?
Yep.
Initial operational capability is when you hang the shingle. That's when the enterprises have already moved in. when we're selling to Congress, and we are, and we can have that discussion elsewhere, but if we're selling to somebody that's going to fund this, we need to say we can start delivering stuff in 10 years for 10 to 15 billion, and then more stuff later. Duh. How many planes did FedEx have? Where's Kevin? Kevin, how many planes did FedEx have at start of FedEx? 3, I think. Right? Good heavens. How many years did Amazon lose money? You know, see, that's all going on in sequence 5. We're all grown-ups here. That's really important to understand that we're not going to leave segment 1 until we're satisfied. Next chart. Thanks. Yeah, next chart. This is all artwork, and I hope you love it. Bill's going to fall on the floor again. The P Swan's going to say, "Oh man," and Michael Lane, stop giggling. Every one of those steps, every one of those sequences has an entrance criteria and an exit criteria, simulation requirement, test data requirement, and you've gone to some senior vice president and said, "Sir, this is how much risk we're buying down by doing this." I have a dear friend, classmate. He says, "Fisher, you never sell anything unless you break or you break or satisfy rule number 1 on the military side." He says, "Explain to me what war you win when you have this and what war you lose if you don't have it." Well, that's what Kevin and Jerry Eddy and Dave Dotson have all explained all morning. And what Vern will say, and we're just doing the same thing vertically, but we got to test and test and test. Okay, I got a couple more cute charts here, and let me go through them. This is going to start instigating questions, but next chart. The simple visualization of the sequences is shown here. We get to IOC. Each one of the steps that I showed earlier has been passed. We exited things, and we got to IOC. And the block before IOC is when we had limited ops, and that's the first flight. Okay, that's the first deliveries and whatnot. Okay, next chart. Now let's go slow here, just so we get the art. Let's suppose we've gotten to IOC. Let's just suppose, and somebody like Michael Lane says, "I need something bigger and faster because this customer needs it." And we say, "We don't make promises, Michael, but this is how we've integrated in an on-ramp logic. This is the adaptive evolution rule that I showed you on chart 1. So when you get to number 3, you take the data out of already performed sequence 3, you go to a new sequence 3, and then you do new steps. So the step before the last green square, you can promise the customer, Michael, that you can do this. And then the parallel with IOC square is the process of integrating it into normal operations of the various Galactic Harbour elevators. Okay? That's what we call adaptive evolution. It's critical. And Adrian, we might need a stronger tether to do some of this. Okay? And et cetera. Maybe we need better surveillance too. Next chart.
Better AI.
Okay, I'm going to skip this one. This is obvious. What I was trying to make a point here is we're going to have parallel ops going on constantly, in my vision of what we're doing here. And this is another master's thesis, Kevin, if you want to work on it. Next chart. Okay, now this is cute. Every one of us in this room has heard of rapid prototyping. Well, this is what rapid prototyping looks like in my sequence thing. Every one of those boxes, right, has entrance criteria, simulation, test, et cetera, et cetera, et cetera. Every one of them requires you go to the senior vice president and get money. But in this case, it's rapid prototyping because you want to insert that adaptive improvement quicker. You dig? All right, now let me go to the next chart. Well, the senior vice president says, okay, I approve the rapid prototyping, but tell me when it breaks. That's a life test. Quote, long-term maturation. That's what that looks like. How am I doing? You getting the picture here? Next chart.
That's cool.
This is when you're doing all that, because that's what you need to do. You got several customers, they have different wants and needs, and then you got to summarize it and put it into an improvement. Now, what's important about this chart is you go to the right, and that's supposed to represent that I've taken a normal improvement, a rapid prototyping improvement, and maybe even a long-term improvement, which is not shown. And I add up the assets, right, that are needed to do. In one case, I got 1, 2, 3, 4, depending on how you I got 4 boxes on top of each other. This gives me a great view of the asset requirements that I need to get through that day or that month or that year. And we've all been in this box or one of those boxes before. What I'm telling you here with express clarity, I hope, that the testing, observational awareness of what we're doing is critical. Next chart. All right. Now here's a story about that somewhat Galactic last thing I told you, and you're going to get test data all over the map. You know. Next chart. My simple argument is you need to put that together in a taxonomic order. And if you don't know what taxonomic order is, oh Lord, Bill Britton, you know what taxonomic order is? This is it. This is what makes it happen. This is the essence, okay, of the operator of the Galactic Harbour. All right, and I think that's sort of my last chart, but there's one more chart. And we'll be doing this for each of the segments, which is what this story is supposed to be. All right, summary chart, I think, is next. That's the operational Galactic Harbour. All right, that's the act, you know, and you got to be up there to do it in most cases. I probably got you ahead of schedule. Sorry about that.
Okay. Pitcher, I have 2 questions for you. Can we go back to chart number 6, Fabio? Way back to 6. Well, you can do that one right there. There you go. That's what we need right there. Okay, Fitcher, you show a dot right here at the entering the engineering verification. What I'd like to do is have you explain 2 questions. One is, how did we get out of box 1? And that's the first thing, you know, that we need to understand as a group. And the second is, what's next in box 2? And those are significant questions. And, you know, you got plenty of time to talk about it.
The engineering validation or verification, whichever word you want to use there, the engineering validation step, verification step, must be accomplished by the builder, because the builder is going to take the information that he learns from all of the tests I was illuminating in the last 10 minutes, all of those, right? And he's going to put them together taxonomically, as I say, and build his or that company's or that corporation's or that joint venture's Galactic Harbour. Okay? So now let's go back one step. Why should somebody be doing all that if he is depending on technologies that are not feasible or provable? What ISEC has done is, frankly, largely an Adelphic approach, and Kevin Berry is the only one in this audience that knows what a Adelphic approach is we've gone around and asked people, how about tethers this? How about CubeSats that? How about sensors this? How about simulations those? Will there be enough of a workforce will there be educational institutions that I can depend on to create the kind of people that can go from 1 to 2 to 3 to 4 here? And the problem we have, I don't know who the we is in that sense, but I'll just leave it there. That we have is China is working that problem, if you know what I mean. All right. And sorry, Kevin, one error on Kevin's charts is they have dismissed carbon nanotubes totally and gone totally to two-dimensional materials. Okay? I see Coleman's comment. Coleman works with the Florida Institute of Technology, and I appreciate your comment. You can depend on them. The question is whether they're going to show up in the magnitude and for the quantity. I think we'll have the talent, but you may not have the experience. You dig? There's an experience thing in here. Okay. Is that enough, Pete? You get my drift?
Well, a lot of technological readiness assessments, preliminary at best, but I mean, we looked at so many things. And so the transition from box 1 to box 2, I think is real. We can stand up and say that we're ready to join the engineering verification. And your point is extremely important, which is that we transitioned from more of a academic arena to more of a testing arena. And of course, the testing needs to be done by technical and large organizations that have real capability to test. You know, an idea of hanging a 1 kilometer meter wide single crystal graphene tether from a bridge and then running a tether climber up and down that's essentially full size, or at least a model. Those types of testing have to be conceptualized, laid out, planned, and then executed. And those are the steps we're looking at now. What do we need to do to enter that second box and get going?
Well, yes, and one of the things we did, and Pete knows this, but for the rest of you, is we took the technology readiness level and we set it aside. And we went out and about, and if we found companies that were working on something that addressed the technological feasibility of the elevator, we said, thank you very much. We won't tell anybody, but we acknowledge your existence. It's called state of the art. In some cases, we found out there were 2 or 3 companies doing it, and that's known as state of the industry. Now, what's important about those 2 differentiations is that these companies are not going out and looking for some sort of badge of accomplishment called a TRL. They're doing it for the corporate profit motivation of a company. God bless them. And I'm proud to say that between Pete and me and Adrian and 6 or 7 other guys on the ISIC staff, we were able to go talk to people. Okay? I still miss Mark Hasse from the University of Cincinnati. He has forgotten more about, two-dimensional materials, except for Adrian. He's a smart man. He's probably, the reason we haven't seen him is because he's working for somebody. That's what we want.
Yeah, it turns out that
we went from box 1 to box 2.
Yeah, you're perfectly correct. We in ISIC were focusing on the reality of what's happening out there. In the first IAA book and then the second IAA book, because it was a global book, they used TRLs as a standard. And we showed that the TRL levels for all the engineering was well along, significantly along enough to enter a program, except for the tether materials. And then that's accelerated rapidly since those books were put to press. Now, it turns out that all of us are sitting here looking at the entrance into the second box. One of the historic points that I like to bring out from my 2 mega projects is When we started those mega projects, we were small groups, 6, 10 people in a conference room saying, yes, we're going to go do it, or thank you for the $1 billion, or something like that. We did not have answers, okay? We had boxes I called scheduled miracles. In the engineering world, when you take on mega projects, there are questions for the future, and you have to address them as significant questions and address them. I'll use one example that I think is so relevant. Turns out in Motorola, when we were doing Iridium in the early days, we came to the conclusion, I should say the technical guys doing the digital switch that would be in space came into the CEO's office of Motorola, so we're talking big time, and said, we can't do Iridium because our digital switch isn't fast enough. So the Motorola CEO said, well, wait a minute, you got to explain that. And they looked at our schedule and had a box there, and we call that miracle number 1. And he looked at it and he says, what are the requirements? And so we laid out the requirements, and he laughed. I mean, this is a CEO of Motorola, laughed at us and said, get out of my room, man. We're going to have that capability in speed and quantity in 18 months. We were not on the to know route. We were not in the processor arena knowing what Motorola was projecting on its capability in digital switches. And so he said, well, do you think if I use the modern modern digital switch, it'll work in space? We all looked at each other and laughed and said, sir, we can make anything you make work in space. And what we meant was have to put a heck of a shielding on the outside of it. But we made those digital switches work. Now, just to put that in perspective, most space programs freeze their design 2 years ahead of launch. Sometimes it's like 6. But anyway, 2 years before launch. We decided for the digital switch that we would wait all the way to 6 months before launch. In fact, they were ready 7 months before launch. But the point is, when we're moving from box 1 to box 2, there are still mega questions that go with every mega project. I'm sorry, Fisher, go ahead.
Yeah. Let me emphasize that a little bit. There are still questions, but what our assessment is that we can resolve it with engineering. But I know most of you on the line here remember that the United States of America was trying to, in 1960, trying to launch a quote spy satellite. The first 13 satellites failed. The first 13 launches of the satellite failed. And it was a combination of launch failures and satellite failures and recovery failures, just imagine. And one of the things that we're going to have to deal with in the Galactic Harbour is to deal with the notion of failure. Now, first of all, I don't like the word failure. I like rather the notion of test insufficiency, because it turns out, especially in today's age of artificial intelligence, that we can learn so much by failures, so much by insufficiencies, so that when you in the world of government, that they're looking for avoiding risk, we in engineering absorb the risk and learn from it. That is an impressively important story. All right. For one, one of my famous lines. I'm sorry, Michael. Here's a famous line for you. There are false alarms, but some alarms are more false than others. And what does that mean? He says, well, I know jumping 98% of the way across the canyon is a quote failure. It's an insufficiency. And that gives us a target for whatever it is that we're testing on what needs improvement. Maybe it's operational, maybe it's material, et cetera. And I know everybody's nodding their heads out there. It's kind of, this is like the bobblehead, kind of a thing. That's what the Galactic Harbour is saying. Let's start that engineering verification, engineering validation activity and get it done by industry. All right. I'm getting to be embarrassed here. I feel like I'm stealing the audience because I want to hear from Adrian and Vern. These are the people that have done it. And we need to get them online here somehow. And Rob too. You've been done it.
Hey, I just want to make sure everybody understands. I was not there in 1960. Okay, counter to your belief. I'm not that old.
I want to say thank you so much to Michael Fitzgerald for that amazing presentation.